I let go, I was a free-floating satellite, just me. And then I turned around so I couldn't see the shuttle anymore. And that was the coolest thing and particularly at night, because I was just, floating. And there's the stars and just me and the rest of the universe. I'll never forget that.
I'm Tali Sapersky, planetarium educator at the Museum of Science, and my guest today is former astronaut and MIT professor Jeff Hoffman. I got to ask him about what it was like to travel in space, what it's going to take to send humans to Mars, and how he helped fix the Hubble Space Telescope. So my big question for you is, what's next for humans in space?
Yeah, well, I can give a big answer. I mean, we got to get back off the planet and onto another planetary surface. It's been over 50 years since humans walked on another planetary surface, the moon. And, of course, lots of reasons for why we haven't done it until now. We're getting ready to do it. There's a lot of, questions about, are we doing it the right way? Do we need to make any changes? One way or the other, humans need to leave planet Earth and start learning about living on other planetary surfaces. The moon is a great place to start. I mean, it's much nearer to us. You can get there in a couple of days. Eventually, we dream of going to Mars. As far as the big question, I mean, there was a book by Oriana Fallaci, an Italian writer, and it was called Someday the Sun Will Die, because her mother, an old Italian woman, asked, why are you interested in space travel? Someday the sun will die. Does humanity want to look far ahead into the future? I mean, we're talking hundreds of millions of years, so not something that I'm going to lose a whole lot of sleep about tonight. But, sooner or later, humans have gone to new habitats. We've learned how to live in other places. And that's a big challenge for us. So for me, that's the next big thing in space.
Well, and you're pretty well qualified to talk about getting off of Earth, considering you did so, 5 times?
Mm-hmm.
5 times, yes. But if there's one mission of yours that people have heard of or that has perhaps the most historical significance, it's probably...
Oh, not probably. It's definitely.
It's definitely the
fixing
Hubble
the
trip.
Hubble Space Telescope.
So you
sure.
are part of the crew that saved Hubble, which just celebrated its 35th anniversary in space. Can you talk a little bit about what it was that was wrong and what it was that you did?
Well, here's the thing. Somehow people are celebrating the anniversary of when it got launched, but when it got launched, it was a dud. I mean, there was a dream of, forward-looking astronomers since the birth of the space age, Lyman Spitzer and others, for putting a large, optically perfect telescope above the Earth's atmosphere. I mean, the Earth's atmosphere distorts images. It absorbs ultraviolet and infrared radiation. We could get an unprecedentedly sharp view of the heavens from above the atmosphere. And that was the dream behind Hubble. Not only that we would put a telescope like that above the atmosphere, but unlike all telescopes and satellites that had been put up before, Hubble was designed to be serviceable by astronauts who would be working from the Space Shuttle hadn't even flown when Hubble was first designed. It was a great leap of faith that we would be able to do that kind of servicing. And Hubble was, there was a lot of press coverage on TV, magazines, all the great things that Hubble was going to be able to do, and the public was enthusiastic about it. I mean, I remember before Hubble was launched, there was really a lot of enthusiasm, and it was launched in April of 1990 to great public fanfare, and gosh, then when you pick up a pair of binoculars, the first thing you do is you take the little focusing thing, you go back and forth, you find the sweet spot. And that's what you do with a telescope. Hubble didn't have a sweet spot. No matter what they did, the images were coming back fuzzy. And it was clear, from optical engineers could recognize from the images that it had spherical aberration. The mirror was slightly the wrong shape.
That optically perfect mirror.
I
It's not
mean,
optically perfect.
people who weren't alive at the time don't appreciate what a disaster it was. I mean, Hubble was denounced in the halls of Congress as a techno-turkey. It was a butt of joke of late-night comedians. This was the time, the early 90s, when NASA was trying to get Congress to approve funding for what would eventually become the International Space Station. And Congress was not happy with NASA. I mean, the basic message was, you guys got to do something about Hubble, and then we'll talk about the space station. So it was critical. Luckily, NASA, the astronomy community, optical engineers, mechanical, electrical engineers, everybody got to work, figured out what the problem was, how it happened. I mean, it's a long, complicated story, and there were numerous red flags, which had people paid attention, we would have discovered the problem, and I wouldn't have gotten to go and fix it, but that's another story. But in any case, we finally realized that there were many ideas of how the optics could be fixed, but we were kind of limited. I mean, we didn't want to bring the telescope back to Earth because it would have gotten contaminated. And I mean, there were a lot of people who were afraid maybe it would never get launched again. We had to put in corrective optics, a bunch of tiny little mirrors, each one the size of your thumbnail, roughly, 2 for each detector inside Hubble. And fortunately, since Hubble was designed to be serviceable, it was possible to do this. And there was a tremendous effort to develop these corrective optics. And of course, once we realized that it was going to be possible to fix Hubble, then within the astronaut office, this was a primo mission, of course, so who's going to be on the flight? NASA wanted to do everything possible to reduce the risk of failure. I mean, we knew that this was critical, and one of the many things that were done was to decide that only people who had previously done spacewalks would be eligible to do spacewalks on Hubble. Here's where a little bit of luck came into my career, because on my very first flight, which was back in 1985, our mission was originally, it was a short 4-day flight to launch 2 satellites, do a few medical experiments, and come home. But the second satellite didn't turn on. And NASA decided to send me and my partner out to do what actually was the very first unplanned spacewalk that NASA had ever done in its history, to go out and try to fix the satellites. So I had my Spacewalkers Union card and was lucky enough to get assigned to the flight. So it was incredibly exciting. And of course, training for the mission, because it was Hubble, we could, anything that anyone could think of to reduce the risk, things that normally wouldn't have been done for a typical flight. I'll give you an example. The original plan, I mean, we needed lots of tools. We had about 200 tools on this flight. We were going to use about half of them, and then we had a bunch of things for backup. And all the tools were in a tool chest at the aft end of the shuttle. So every day we'd go out the airlock, we'd translate back to the back of the shuttle and put the tools onto our tool carrier and then go do our work. And then at the end of our work, we'd go back, take the tools off, put them in the tool chest, and come back to the airlock and get inside. And just handling these tools and going back and forth was taking 20 or 30 minutes out of a limited time outside. I mean, a spacesuit it's designed for about 6.5 hours. You can stretch it to about 8 hours. So we suggested, I don't know exactly, probably about 6 months or so before the launch, if we had these tools inside, we could save that time and we'd have more time outside to do useful work. Because every flight you have what we call a limiting consumable. Our limiting consumable on Hubble was EVA time, spacewalking time outside, and we wanted to maximize that. Well, normally they say, we've done the weight and balance. I mean, it's there, it's already installed. Forget it, just deal with it. But no, this was Hubble, and sure enough, the tools got brought inside. And on our very first spacewalk, the first of 5, we had a problem that after we had replaced the rate gyros, the big door wouldn't close. And it took us about an hour to
The door
analyze.
on Hubble
The door on Hubble.
wouldn't close.
Took us about an hour to diagnose the problem, figure out how to fix it. And we were out for just about 8 hours. So we really needed that time. And that was just one example. Everybody wanted Hubble to succeed. You know, sometimes you hear about intercenter rivalry at NASA. No, nothing like that. Everybody was on the same team, and it was an incredible experience. I do remember we did a lot of training at the Marshall Space Flight Center because the Johnson Space Center, where astronauts normally are located, didn't have the big underwater pool yet at that time.
Oh, it didn't? Okay.
No, at that time we did our EVA training in a swimming pool, which is fine. You could put a shuttle payload bay in that, but it wasn't deep enough for Hubble, which is 50 feet from top to bottom. So at the Marshall Space Flight Center in Alabama, they had a deep pool, 50 feet deep, and that's where we did most of our training. They had the models of Hubble up there. So, yeah, we'd go up there. We'd spend the whole week. Every day, one team would go in. There were it wasn't just the corrective optics on Hubble. I mean, there were many other problems. The solar panels were vibrating every time it went from night to day and day to night because of thermal stress. And then, I mean, a tape recorder had failed, some other electronic boxes. In all, there were about a dozen things that we had to do. Mm-hmm. And when they went through and sort of did the timeline, they realized it was going to take 5 spacewalks. NASA had never done 5 spacewalks in a mission. People thought, well, maybe that was too much for 2 people. And so we actually had 2 spacewalking teams. And my partner, Story, and I went out on days 1, 3, and 5. And Tom Akers and Kathy Thornton went out on days 2 and 4. This was the very first day that we went out. We had that problem with the door. And, of course, you can imagine this was the very first task we did. And when the door wouldn't close, and knowing that if the door doesn't close, we lose the telescope, light comes in, the heat comes out. So it was a great relief when we finally got inside and that had worked. And in fact, all of the 5 spacewalks managed to do everything we had set out to do, plus one other task, because we went up to the top of the telescope on the 3rd day of spacewalking after we had installed the first of the corrective optics. And I know that, before becoming an astronaut, I was an astronomer. So I had a lot of astronomer friends who had called me before the flight because, everybody knew what a complex mission it was, all the things we were trying to do. And, the common question was, Jeff, can you guys really do all that? And I said, well, we're going to do our best. And so I knew when we had installed the wide field planetary camera that the whole astronomy community had let out a breath of relief because finally we hoped that things would work. Of course, after the 5th and final spacewalk, we realized that we had done all the work that we had set out to do. Despite the fact that a lot of people had thought that the mission was too complex. At one time, they were talking about downscoping the mission. There's too much that we're asking the astronauts to do. But we got it all done.
Thinking of splitting it into 2 missions?
Which wouldn't have made sense. Because it may well have been that 1 or 2 of the tasks wouldn't have worked, but nobody knew what that would have been. So suppose you took half the task and put it on the first mission, and those were the things that didn't work. Anyway, we got it all done. But, of course, nobody knew would the corrective optics really work like they were supposed to.
So when did you find out
what happened was you can't turn on all of the detectors right away because they had come up from the Earth and there's a little bit of atmosphere which sticks to the outside and you have to wait until that evaporates because if you turn on the high voltage and there's just a little bit of gas around, you'll get sparks and, the high voltage,
bad things. Bad things happen.
You've blown your electronics. So it really wasn't until the end of December that they could start turning things on. And I'll never forget, it was New Year's Eve. We had just had some people over for a party, and I was cleaning up a little after midnight, and the phone rang, and it was an old friend, astronomer friend from the Space Telescope Institute in Baltimore. We wished each other Happy New Year. Jeff, you have any champagne left over? Yeah, I have a half a bottle in the refrigerator. Okay, he said, pour yourself a glass. We just got the first pictures back from Hubble, and it worked. And of course, the rest is history, because Hubble has gone on to really rewrite astronomy textbooks many times over. And from studying the planets to stars in our galaxy to other galaxies, and then for me, probably the most precedent-shattering discovery was when they tried to measure the rate at which the expansion of the universe, which had originally been discovered by Edwin Hubble, after whom the telescope was named. But everybody knew that the universe is expanding, but all the mass inside has gravity, and so the expansion will be slowing down. But how fast it's slowing down is important. It gives you a measure of the mass inside the universe and so on.
Oh, but wait.
And there were two teams which were given that task, analyze it and come out with an answer. And they didn't publish for a long time. And everybody was wondering what's going on. Finally, they got together, compared their results. And the reason they hadn't published was because they figured we must have made a mistake, because what we found out is that the acceleration of the universe is not slowing down, it's speeding up, which led to this concept there must be this thing which we call dark energy. I mean, it totally upset our notions about cosmology. Dark energy, I mean, it's great to give it a name because it makes it sound like you know what you're talking about. But really, we don't have a clue. And we're still doing a lot of studying about the history of dark energy throughout the history of the universe. I mean, it's really led to fantastic new developments in our understanding of the structure of the universe that we live in.
I mean, Hubble's really good at that. So, like, for astronomers, there's kind of, there's before Hubble and there's after Hubble, right? There's this paradigm shifting thing.
You talk about the 35th anniversary. That's the 35th anniversary of the launch. And I really think we should be celebrating the anniversary of when Hubble actually got fixed.
Of your mission.
We celebrated it, But in any case, the other thing to realize about Hubble, when the Webb telescope was put up, I think there were a lot of people who thought that this was somehow a replacement for Hubble.
You did read that a lot. This was Hubble's,
in fact,
the next generation.
Well, it is certainly the next generation telescope, because Hubble was made with the telescope technology of the mid-20th century, the big hunk of glass, which was the main mirror. Astronomers on the ground towards the end of the 20th century learned how to make multiple mirror telescopes, so you could make them much larger, much lighter. And that's the way Webb was made. But Webb looks primarily in the infrared, the heat portion of the electromagnetic spectrum, whereas Hubble can look all the way into the ultraviolet. So in a sense, Hubble now is even more valuable. Together with Webb, they span this broad section of the spectrum. And so Hubble, the other thing to remember about Hubble is it really showed the value of servicing. I mean, when people think about servicing, most people probably just think about, oh, yeah, they went up and they fixed Hubble. The important thing to remember is that there have been 5 servicing missions, and every time we've gone up to service Hubble, we've taken out old detectors and put in new, more powerful detectors. I mean, that was the dream behind Hubble. That's what we do with telescopes on the ground. The mirror stays the same, but we're constantly developing newer, more powerful detectors. And so Hubble now has almost 1,000 times the sensitivity of when it was first launched because of all the new instruments were put in. So, that's the real value of servicing.
All right. You are an astronomer and a space nerd. I am also a massive space nerd. So what was it like to touch Hubble?
The biggest thrill of a lifetime. I mean, as an astronomer and astronaut, to put my hands on the Hubble Space Telescope and, of course, be able to fix it, something I'll never forget. And, of course, the experience of just being up there, probably the most memorable was I was at the top of the telescope because we were fixing the magnetometers. The magnetometers, they're simple instruments, and they had two of them. So they figured, magnetometers don't fail, and we have two of them. So they didn't design them to be replaced.
And then
They both failed in the first 3 years. I mean, incredible. So we went up with new magnetometers. We had to basically put them on top and then take the wiring off the old ones and rewire the new ones, and that worked. But on the fifth and final spacewalk, I was actually what we call the free floater. One of the two of us were always had their feet in the foot restraints on the end of the robotic arm, which is nice because when you're carrying around big pieces of equipment, the arm moves you around. And I did that, for instance, when we put in the wide field planetary camera. I was standing on the arm and I put it in, and Story was sort of helping with his feet in a foot restraint. But up at the top of the telescope, I wasn't in a foot restraint. I was just sort of holding on with one hand. And I remember thinking, I wonder what it will feel like if I just let go. Now, I was tethered, okay, but the tether was loose, so it wasn't pulling on me. And it was really strange because, I was holding on. I said, all right, let's let go and see what happens. But I didn't let go. Well, all right, let go. But I didn't there was some part deep in my reptilian brain, I think, that, the ground is a long way down there, 400 miles.
Maybe you shouldn't let go.
Well, but I said, come on, stupid, let go. So I let go, and it was amazing because it was a psychological transformation. When you're holding on, you're part of the shuttle system. I move back and forth. I'm pushing against the shuttle. And somehow I let go. I was a free-floating satellite, just me. And then I turned around so I couldn't see the shuttle anymore. And that was the coolest thing and particularly at night, because I was just, floating. And there's the stars and just me and the rest of the universe. I'll never forget that. That was an incredible experience.
That sounds amazing. So you've been to space several times.
5 times.
5 times. What is it like? And you have these sort of existential moments. What do you think going to space can teach us about being human?
If there's anything that I would like people to understand from seeing pictures that we take from space about, the curvature of the Earth, the thin atmosphere, it's that we're all citizens on one planet, a sense of living on a finite planet. You go back in human history. For my third space flight, I was working on the tethered satellite project, which was a joint Italian-American project. So we spent a lot of time in Italy, and we were in Florence. I was learning a little bit about the history. And, back in the Renaissance time, they had these two families within the city, the Guelphs and the Ghibellines, and they were fighting each other. And then, sort of they made peace because Florence as a city had to fight against Siena, with the next city. And then gradually the cities came together and became part of a country. And we're still in the stage of human history where, we're citizens of countries and we think of ourselves as Americans, and then there's Chinese and Russians and French and, Brazilians and what's our identity as human beings? The other types of identity are different religions, you Catholics, Protestants, Jews, Buddhists, Muslims, and so on. Ultimately, we've got to realize that we're all here citizens on planet Earth. We share a finite planet. And if there's anything I wish that people could get from these images that we send back from space, it's that we don't live in a flat Earth. The Earth is round, okay? And sure, everybody knows that intellectually, but
you'd be surprised.
Well, but to appreciate what it means to live on a round Earth means we're living on a finite planet. The human population grows; the size of the planet does not grow. We're sharing a very unique place in our solar system. I mean, that's one of the things that I think People sometimes ask me, why do astronauts come back from space and talk about we need to preserve the Earth and the Earth is fragile? And I think the unique thing about the astronaut's point of view is, there I am in orbit, floating, looking out the window down at planet Earth, but on the outside of that window is a vacuum. I go out there, 10 seconds, I'm unconscious, and then pretty soon I'm dead. You realize most of the universe is totally hostile to life. And then you look down at this beautiful blue and green and white and brown planet that has given birth to life and sustains life. And I think that really gives you a sense of love for planet Earth and the need to protect the Earth because, we see the Earth from that point of view. And again, it's intellectually, you realize that, but somehow to actually see and experience something physically, it's like we all have seen pictures of the Grand Canyon, and it's beautiful. But man, when you're down there at the river and you look up at, millions of years of geological history, it affects you emotionally in a much deeper way. And that's, I think, the same thing about being in space and looking back down on the Earth. And over, people who go up, even the people who go up on these short suborbital flights and look out, when Captain Kirk went up and, he was moved to tears, he said, just looking back at our home planet. So, you ask what about space can make us more human? It's that we're part of the human race, which is inhabiting one planet. And I'd love for people to have that sense that we're all on the planet together and we need to take care of it. It's the only planet we got right now.
So having been in space and having felt these things and experienced these things, is it difficult at all to readapt to life back on Earth?
Oh, I get a lot of help on that. When I came back from fixing the Hubble Telescope, the first thing after we came back home, walked into the kitchen and my wife pointed at the washing machine and said, "All right, Mr. Hubble repairman, while you were up fixing the Hubble, the washing machine broke. So go get your toolkit. And by the way, the grass out of the back lawn didn't know that you were up in space. It kept on growing. So there's the lawnmower." So, life goes on. I've been fortunate. I have a good family life. And so I had no problem readapting. But of course, back in my mind, I have these incredible memories and visions of what it was like being up there, which I'll never forget.
Were you, in fact, able to fix the washing machine?
I was. And I did mow the lawn.
So you've been talking about how, it's important for humanity to move on to other planetary surfaces. And of course, we've got Project Artemis right now trying to get us to the moon. But we do have our eye on Mars. Mm-hmm. And in your, moving a little bit to your post-astronaut life at this point, you were involved in a very fascinating project that has to do with potentially how humans can maybe one day exist on Mars. Do you want to talk a little bit about MOXIE?
Yeah, sure. Because Mars, unlike, the moon, we will go to the moon. I think there's a lot of valuable things we can do there, both scientifically, possibly using lunar resources. But the moon lacks a lot of critical elements for life, whereas Mars has all the elements that are necessary for life. And not only that, but from everything that we know now about Martian history as a result of all of the probes that we've sent orbiting Mars, landing on Mars, the rovers, and so on, we think that in the early part of the solar system history, Mars was probably very much like the Earth. Mm-hmm. Maybe had a lot of water on it. We don't really know for how long, but what we do know about the Earth is that as soon as liquid water formed on Earth, once things settled down after the initial chaos of the early solar system, and the Earth had water, oceans, and life evolved very quickly.
Yeah.
Did that happen on Mars? The search for life. You asked me before about the big question, and,
Yeah.
that's the other big question: is life in the universe? And we could talk about that. But Mars definitely looks like it had the conditions similar to Earth where life evolved. Of course, Mars lost its magnetic field. It lost its atmosphere. It's now a cold, dry desert.
Not such a great place these
Well,
days.
the surface of Mars is certainly not. It's bombarded by solar ultraviolet radiation, cosmic rays, and so on. So, Viking went to look for life on the surface, didn't find any. Not too surprising in retrospect. But underground, who knows? I mean, if single-cell life evolved on Mars, and let's remember on Earth for like the first several billion years of life, it was just single-cell organisms until things got a lot more complicated. So if there was life on Mars, there's probably only single-cell life.
Mm-hmm.
But we also know here on Earth, there's bacteria that went underground, and we have bacteria that are, fat, dumb, and happy a mile below the ground. They've learned how to metabolize minerals from rocks. You need a little bit of liquid water. And underground on Mars, I mean, maybe there's still life or at least fossil remains of life. And that's one of the things that we'd like to look for with digging on Mars. I mean, the Europeans are going to send the ExoMars, which can dig about 2 meters. But if we want to go deeper than that, we're going to need some rednecks, oil rigs and that sort of thing. And of course, to really explore Mars, which is such a fascinating planet. I mean, everything we've learned about it, the more we know, the more interesting it is. We need to explore it as well as is humanly possible, which ultimately means with humans. Once we go to Mars, I mean, Mars is hard. It's a long way away, much farther than the moon. It's not a 3-day trip. It's more like, with current rocket technology, more like 7 or 8 months. And, maybe nuclear propulsion will get us there in 3 months. But one way or the other, it's a long way away. And, of course, once you get there, you're going to do some exploring, but I assume at least the early explorers are going to want to come back home.
You'd think, yeah.
Yeah, well, I mean, some people have talked about one-way trips to Mars, and not for me, thanks. But to get back from Mars, you need essentially as much rocket propellant as you needed to get there. And rocket propellant is a fuel and an oxidizer, and we think the fuel will probably be methane and liquid oxygen. Well, we can, we're rocket scientists, okay? We can calculate how big a rocket you need to get 6 people off the surface of Mars. And you're going to need about 30 tons of oxygen for that rocket.
And it's impractical to bring that with you.
Well, you can do it. I mean, there's a lot of stuff we're going to have to bring to Mars. I mean, anything that's manufactured, spacesuits, computers, right, we're going to make on Earth and we'll bring it to Mars. But dumb old oxygen? I mean, here's the problem. To bring 1 ton of anything from the Earth to the surface of Mars, you've got to put about 15 tons of stuff into Earth orbit. Most of that's propellant, but, rocket body, rocket motors, heat shield. So, as I say, we have to do that for any manufactured goods. But, the total amount of mass that we think we would need for an initial expedition to Mars is, many tens of tons. So 30 tons of oxygen, that's a large fraction of what we need. And to get that 30 tons to the surface of Mars, if you have to put 15 tons in Earth orbit for every ton to Mars, you're talking about 450 tons of stuff in Earth orbit. And I mean, the Saturn V could put about 120 tons. 3, 4 Saturn V launches at, a couple of $1 billion a shot. I mean,
Just for the oxygen.
Starship that SpaceX is making hopefully can do it a little bit cheaper, but still, to bring dumb old oxygen all the way from the Earth to Mars just so you can come back makes no sense if you could produce that oxygen on Mars. Mm-hmm. And that was the point of our MOXIE experiment. When I was first taken into the astronaut office back in 1978, it was 6 years after the last Apollo mission. And we all thought, oh, yeah, it's just going to take another president like JFK, and he's going to say, yeah, let's go to Mars, and we're going to do it. And, some of us here are going to actually get to Mars. Well, that never happened. I mean, we haven't even gotten back to the moon yet, much less Mars. So I'm never going to make it to Mars physically. But it was really exciting when I was invited to be the deputy principal investigator of the MOXIE experiment. MOXIE is an acronym, the Mars Oxygen ISRU experiment. It's really a nested acronym because ISRU is another acronym, which means in situ resource utilization, which is a fancy way of saying, let's live off the land, which is what explorers have done, since time immemorial. You're sailing across the ocean, you come to an island. Yeah, you get water, food, you restock. And
so what you're saying is you really wanted it to be named MOXIE.
Well, it came pretty obviously. And when you start with Mars Oxygen, MOX, and then ISRU, I mean, yeah. And of course, MOXIE, not only is it a soft drink, which, by the way, was developed here in Massachusetts originally.
I did not know that.
In Lowell, Massachusetts. They still make it. It's up in Maine.
Lowell, shout out.
We were a little concerned actually if we named it MOXIE, as the soft drink company could have a problem with that, but they loved it. Actually, they have a MOXIE parade up there in Maine every year, and we got invited to go up and be in the MOXIE parade and everything. But that was a fun part of it. But the idea of MOXIE. There's no free oxygen on Mars.
It's carbon dioxide.
Mars does have an atmosphere. It's very thin. It's about 1% of the density of the Earth's sea level and atmosphere. It's about the same density as if you went up to about 100,000 feet, 30 kilometers above the surface of the Earth. So not enough pressure even to sustain liquid water on the surface of Mars. But it's there. And carbon dioxide, of course, CO2. So there is oxygen. It's just bound up in carbon dioxide. And what MOXIE did, this is a chemical process which was developed here on Earth in laboratories. It was tested many times. Just like in high school chemistry, we all electrolyze water. You put the 2 electrodes in, you hook them up to a battery, and hydrogen comes out one side, oxygen comes up the other side. Well, it turns out you can electrolyze carbon dioxide. It's a lot harder. You have to heat it up to 800 degrees Celsius. You have to run it over a catalytic bed with nickel and some rare earth catalysts and, a whole bunch of complex things to do the process. And this was developed in laboratories here on Earth and tested many times. But NASA has a rule. If you're going to rely on a piece of equipment or a process that's critical for a mission or for human life, and certainly making oxygen if you go to Mars, yeah, that's pretty critical. You need to demonstrate it in the actual environment in which it's going to be used, and that means we had to take this chemical process and show that it works on Mars. We fully expected that it would, but, maybe Mars had some surprises in store which nobody thought about, those unknown unknowns. And so we basically, with working together with the Jet Propulsion Lab, this was a joint Jet Propulsion Lab MIT experiment. Jet Propulsion Lab built the MOXIE hardware, and they turned it over to us once it was launched and on the surface of Mars.
Which
we operated it.
It was in the Perseverance rover.
MOXIE was one of many experiments which was taken to Mars by the Perseverance rover. It was launched in the summer of 2020. Landed on Mars in
2021.
February of 2021. And in April, actually, there were 2 historic events. On April the 19th, it was this Wright brothers moment where the first flight of the Ingenuity helicopter, which, I mean, when you think about it, this was the first controlled flight of an aerodynamic vehicle in the atmosphere of another planetary body. I mean, that's Wright brothers stuff. This was incredible. And the very next day was the first time that oxygen was produced on Mars, basically by using local resources to produce a valuable asset for future human exploration. Obviously, we just measured the oxygen we made and for its purity and its amount because there was nobody there to use it. Moxie was just a test. I mean, it was a much smaller scale. If we could run Moxie continuously at full force, we could make about 4 grams per hour, maybe up to 12 grams an hour maximum, which is enough maybe to keep a small dog or cat alive, which we didn't have on Mars. So we just measured the oxygen, released it back to the Mars atmosphere. But someday, if we have a human mission and you really want to use a Moxie-type technology to produce the oxidizer you need for the rocket, which is going to take the crew back up from the surface of Mars into Mars orbit to get their ride home, you're going to need something orders of magnitude bigger than our Moxie experiment.
Super Moxie.
A super Moxie, which would produce about 3 kilograms per hour, is what we figured we would need to load up a rocket in the time. We can only get to Mars every 26 months because Mars goes around the sun every 2 years, the Earth goes around every 1 year, and we sort of come close together every 26 months. That's when we can go to Mars. And so between each 26-month period, we could land a rocket on the surface of Mars. It would land having used up all of its oxygen, ready to be refueled so that the crew who comes 26 months later would have that rocket ready to go back. And to fuel it up in time, we have to make about 3 kilograms an hour. The thing about electrolysis is it does take a lot of electrical energy. I mean, when we ran Moxie, we could only make oxygen for about an hour because you would use up all the battery power on the Perseverance rover. So then we had to shut down and they'd recharge the batteries for all the other experiments. To make 3 grams an hour, you probably need about 25 kilowatts at least of electrical power, which probably means nuclear power. Doing that, you could do it by solar power, but it's problematic on Mars. So one way or the other, we need a lot of electrical power, which you also need, to keep a human habitation going on Mars, you also probably need about 25 kilowatts. So the dream is, if we have a power supply, nuclear or whatever, when there's nobody on Mars, use it to make oxygen. Now the people come, switch it over, supply the habitat. There's a lot of different ways you can do it, but the point is Mars exploration is going to take a lot of electrical power, and part of that's going to go to make oxygen. And now we know that we can do it.
If you had to make a prediction when humans could make it to Mars.
I never answer that question. I'm
question.
sorry, because it depends on things that I know nothing about. I mean, Elon Musk says we can do it in 2 years from now.
I'm skeptical.
I'm waiting. I'm a bit skeptical. It's going to be expensive to do it safely and successfully. What will it take for the country to make that commitment? Or can we get other countries to come along and share the expense like we're doing in the Artemis program? We'll do it someday, I'm sure. I hope I'll be alive to see it. I'm 80 now. I'm still healthy, so I'll hang around. I'd love to see people land on Mars. I'm not going to get to do it myself. I was very fortunate, at least, to be a part of an experiment which ultimately will help human exploration of Mars. And I'd love to see it, but I don't know when it's going to happen.
Would you go?
Interesting question. If I thought there was a reasonable chance of survival and coming back, yeah. I mean, People ask, would I like to go in space again? Yeah, I mean, space is great. I'd love to do that and to get to explore another planet. I mean, the first people, it's not going to be me, okay, but the first people to go to Mars, I mean, again, that's like the Neil Armstrong moment of stepping out on the moon, the first human on another planetary body. And Mars is, a step beyond, a big step beyond. So it's going to be exciting, difficult, expensive, but exciting.
Getting, say, robots to Mars, like Perseverance or maybe even something more advanced, is expensive, but it's not as expensive as sending humans. So do we need to send humans to Mars?
You get what you pay for. That's true in space travel. People somehow think that robotics are more advanced than they really are. I mean, I love robots in space. There are always going to be places that people can't go, and the first thing we do is we send our robots there, and they've done incredible things. And I'm very enthusiastic. We'll continue to improve, but somehow people have the idea that we can have a robot with artificial intelligence that can do everything that a human can do. I mean, we're still trying to understand the future of artificial intelligence and how it will affect our life here on Earth. I mean, if we ever get to the point where we truly have humanoid robots that can do everything that a human can do, civilization will have changed so much that I don't even want to try to predict it, what effect that will have on our lives. But right now, there's still, particularly when you're doing things like exploration. I mean, our robotic vehicles are great for doing what have been designed to do. Perseverance was designed to look at the geology and potential early biology capabilities on Mars, to dig, to get samples that hopefully we'll someday get back on Earth to analyze. And that's what it does. When the astronauts were on the moon, they found things that hadn't been planned on, and they could adapt. They could do different things. I mean, when we were up fixing Hubble, there were some things up there that a properly designed robotic system could have done, to put an instrument in and take it out. But man, when those doors wouldn't close, we tried to explain to the people on the ground what was going on, but they just didn't have the same situational awareness that we did on the spot. The human mind can deal with contingencies, with things rapidly changing. As I said, if we ever get to the point where we have robots that can think as well as humans, and maybe we will, our lives here on Earth will be much different, not just planetary exploration. But for now, robotic exploration is so slow. I mean, Perseverance and the other rovers that we've sent to the moon and to Mars, these are incredible machines, and we can only use them at a fraction of what they would really be capable of doing. For a couple of reasons. I mean, first, you have the time delay. I mean, we ask Perseverance to do something, so we send up a bunch of commands, and then the next day it does whatever it's been commanded to do. Then we have to get all the information back to see what it actually did, what state is it in, did anything fail. You analyze that, you make another set of commands. So you got a couple of days going back and forth, and on each day it can maybe move maybe a few hundred meters. It's faster than the other rovers, but a heck of a lot slower than somebody walking around. My dream is not to replace robots with humans, but to put humans and robots in the same environment. I mean, because the other thing about Perseverance and the other rovers is we have to operate them so conservatively, because, I mean, if they get stuck in the sand, there's nobody to dig them out. If if one of the wheels breaks, there's nobody to change a tire. If you had astronauts on Mars who could control those rovers, they could joystick them in real time. They could go much faster. They could do so much more than we can do with them now. And we could operate them a lot more aggressively, because if they did get stuck in the sand, you could dig them out. And if something breaks, you can fix it. So that's really my vision for future exploration on planetary surfaces is let's get humans and robots in the same environment so that we can take full advantage of whatever the robotic capability is at that time, and have the humans and robots working together. That's what I hope we'll be able to see before too long.
So as you look back at your career, which is ongoing, you've led a very interesting life.
I've been very fortunate.
You've not just gone to
I
space.
have to say.
You've gone backpacking all over the world. You got to send an instrument to Mars. You've got to mentor students. You get to do you've done all these amazing things, and you're still doing them. If you had to sort of look back at what you've done so far, and pick out the thing that means the most to you.
Well, professionally, of course, having fixed the Hubble telescope is something that everybody recognizes as having made a huge impact. Mm-hmm. But I have to tell you, now as a professor at MIT, the thing that gives me the most pleasure is when I see my students succeed. And I had a student who was, I taught her as an undergraduate, and I supervised her master's thesis. She went on to get a doctorate. She's now the department head. I work for her now. I mean, what a thrill to see your student succeed, and now she's my boss. And I've had other students who have gone on to do really great things. And when they come back and thank me for having inspired them and guided them, I mean, that, gives you a warm feeling inside, because they're the future. Hopefully I have a few useful years of work left in me, but it's the students who will carry on the work. And I think that's a pretty universal feeling among teachers is we love to see our students succeed.
So I am going to sort of wrap this up with a total out there question that's going to go back to, you and I have known each other for years at this point, but this was back when I had just started sending you emails asking if you wanted to work on something with us. And it was the first time you were coming to the museum for a meeting with me, and you had to cancel because...
When was this?
Oh gosh, years ago. You had to cancel because you had ridden your bike to work and it had started downpouring. And so getting here would have meant riding on the subway. And you were like, can we maybe just reschedule instead? So I remember thinking at the time, spaceflight, Boston subway. Which one's scarier?
Or riding my bicycle on, actually Boston streets are a little safer now for bicycles than they were back then. My college classmates in our alumni magazine wrote something about me, and this is when I was an active astronaut. And even at NASA, I used to ride my bike to work every day, and so they pointed out how, here's Jeff Hoffman, who he's training to ride on humanity's most advanced transportation system up into space, but he still commutes to work by bicycle, which I still do every day, rain, shine. I'm kind of surprised that I canceled because of a downpour. Maybe I wasn't dressed for it, because usually I have good rain gear now. So even when it's raining, when it snows, I ride to work every day, rain or shine or snow or whatever.
All right, I lied. One more question. Since you brought it up, training to ride the most, advanced, what was at the time the most advanced transportation system in human history, which was the Space Shuttle. I've seen video, obviously. I've never seen a launch in person. What is it?
You got to go down there sometime.
What is it like to launch
into space? it's an overpowering thing, even for spectators. I mean, I always remember from my first launch, a lot of my family came in, including one of my uncles who he was a high-powered New York lawyer, didn't get fazed by anything. Apparently, he broke down in tears when he saw the rocket going up with little Jeff going up in space, because even for the spectators, you're 3 miles away. The ground is shaking. I mean, the first you see the flame come out, and the sound doesn't hit you until 15 seconds later. But the air, you can feel your chest vibrating. The ground is shaking. So imagine what it's like inside the shuttle. I mean, people told me before my first flight, and so what's it going to feel like? Because we're in the simulator, and they shake the simulator as much as they can, but they don't want the nuts and bolts to come apart. So people said, forget the simulator. I mean, that's nothing like the real thing. They said, imagine as much vibration and noise as you can, because it's going to be worse than that. And sure enough, I mean, it's just going through the countdown is exciting, but those last few seconds, 10, 9, 8, and then the way the shuttle worked at 6, the main engines would come on, so you'd feel that rumbling down below. But the real power for the shuttle came from the 2 solid rocket boosters. And a solid rocket booster, it's solid fuel, and there's a big hole down the middle where the exhaust comes out, and there's a lot of turbulence there. And that creates tremendous vibration. So, as soon as those boosters light, and, I'm looking out the window, and the ground is falling away, and everything is shaking. And look, we have our helmet visors closed, because otherwise the noise would be deafening. But, I mean, it's just shaking. And sure enough, I said, wow, I wasn't expecting this. And then you're going straight up. You break the sound barrier in about a minute going straight up. And, of course, when you go transonic, you have the shock waves from breaking the sound barrier, so the vibrations got even more intense. And I was thinking, this can't be normal. The wings are going to fall off or something. I mean, obviously, I knew intellectually, because I think we were the 16th shuttle flight, and 15 shuttles had launched, and the wings had never fallen off. So I knew
that
intellectually,
again.
But yeah, I mean, it was wild. And then, of course, after 2 minutes, those boosters would fall off, and then it's very quiet, and you're basically burning hydrogen and oxygen in the liquid engines, and you just sort of sit back, and the Gs build up. And on the shuttle, they only built up to about 3 Gs. Not particularly comfortable, but you can tolerate that. But then the magic moment is after about 8.5 minutes of this incredible experience, like nothing I had ever experienced before. And all of a sudden it gets quiet, and I feel myself sort of floating up in my seat. And of course, I had a lot of experience in the zero gravity airplane. So this was this strange thing in my head was, after this incredible launch experience, now all of a sudden I'm weightless, and I had the feeling, oh, now I'm back in an environment that I'm used to, because I've been weightless before. But the thing about the plane is you're weightless for about 30 seconds, and then you pull out at 2 Gs. Mm-hmm. And of course, when you're in there, you have to get back down either in your seat or on the ground, because you don't want to be up in the ceiling of the plane when the Gs come on, And so what I realized after about a minute was I was waiting for the pullout, and that's when it hit me. No, stupid, there's no pullout. You're in orbit. And so that's when I floated out of my seat over to the window, and there's the coast of Africa coming over the horizon. And that's when it really hit me, after dreaming about riding in a rocket since I was 6 years old. And, my heroes back then, there were no real astronauts, but, Flash Gordon, Buck Rogers, and they rode in their rocket ships. And I'm finally in space. Boy, I couldn't stop smiling for hours after that. That was something I'll never forget.
Well, I can't think of a better note to end on than a wildly grinning Jeff on his first flight up into space.
Well, I still remember it. You can see I'm still smiling.
Thank you so
Great
much,
talking
Jeff.
with you. Yeah, it's been
I always
fun.
love getting to talk to you, and we always love having you back in the museum.
Always fun to come back.